Hello everyone and welcome to this presentation in which I'm going to be talking about steel column supports. In other words, steel column base plates and foundation, and if we should assume them to be pinned, rigid or semi-rigid. And in this video I'm going to be not just giving you the usual answer of it depends, but I will actually give you some references that can help you understand why it depends and when you actually can assume it to be fixed, as well as the consequences of assuming fixed versus pinned on the concrete foundation upon which the steel plate is standing on. This video relies heavily on a reference at the Steel Construction Info, which is this report, which I will be linking in the video description, and it's free for you to download and take a look. This report has been endorsed by a multitude of universities, as I will show you in this video. So without further ado, let's dive into the video. So sit back, relax and enjoy the show. Alright, now let's cut the fluff. Is it fixed, which also is called stiff and rigid, or is it pinned? Well, the typical answer is it depends on. And this answer, it depends on, is not just a dodge or something that people tell you just because they don't know. No, in fact, it really depends. It depends on the base plate stiffness versus the column stiffness, because if you want to hold a column in place, you would need to be able to grab the column in place. So the base plate stiffness becomes an important factor, and it should be more than the column stiffness to be able to control the column and stop it from rotating. But that's not enough, because the base plate is not just suspended in mid-air. No, this base plate is connected to a concrete foundation. So suddenly the foundation stiffness itself comes into play, and the foundation soil interaction comes into play. Because if you see the top view of a foundation, if you apply a moment and an axial force in the foundation, then suddenly only part of the foundation area is under compression, and you have to check out if the soil interaction works or not. Finally, this foundation is not also suspended in space, it is on soil, so the behavior of soil comes into play. So when people tell you, hey, it depends, it actually depends. Roll the credits, we're done. No. Luckily, the Eurocode talks about it and tries to classify the column base plate based on a multitude of criteria. But before I dive into this topic, there are some economical considerations you have to think about. Now, the first question is, why would you even put a fixed support under a column in a frame? You would do that because maybe you are unable to control the story sway due to the loading, or maybe the columns got so large because of the moments. Because if you have a simply supported frame, then the moment diagram looks kind of like this. But if you have a fixed frame, then this moment diagram becomes smaller because part of the moment shifts as the support carries it. Meaning that fixed supports can lead to saving in the sections of the columns and of the beams. Furthermore, if you have a rigid support, then the sideways deflection of the frame due to wind load, for example, is reduced because suddenly you have a fixed support that helps you. Also, it may have an effect on the deflection of the span of the beam. So there are positives. However, there are also negatives. Because if you make a rigid support at the column, at the base of the column, then this means that this steel section traditionally will have to have steel plates or stiffeners attached to it. Now, usually those columns get prefabricated in a factory and they just get erected in the site. You think that it's easy because you can simply put a stiffener here and make it rigid. Well, that's true on paper. However, in reality, you have a steel vendor who you are gonna be buying steel sections from. If you ask the steel vendor to provide you with the stiffened steel columns and base plate, this will increase the cost because there is nothing ready at the steel vendor like this, and he suddenly must have new plates and stiffness to the column. This will increase the cost and increase the time. And even if you bring it in your site and then decide you want to weld those stiffeners yourself, you would still have to deal with the extra cost of welding. Furthermore, sometimes you would have, for example, a box like this as a column, and if you weld some stiffeners, then the box might buckle. So there are all kinds of consequences that you need to take care of that may increase the cost itself. Furthermore, when you have a base plate that is under moment, then part of those bolts is gonna be under tension. What I mean by this is, if you have a base plate under a column that is fixed, then suddenly this fixation means you have moments. And the moment transfer between the base plate and the foundation happens by a compression force, which is the base plate bearing itself on the foundation as well as a bolt here, and a tensile force on another bolt. This means that this bolt, let's say this one, can be plugged out of the foundation, and this will need you to pay extra attention on the type of bolt used and the bolt sleeve that is used. It becomes an extra cost and extra calculation for you. Furthermore, if you apply a fixed support, then suddenly your foundation becomes fixed, which means that the foundation itself will have axial loads and moment, causing the foundation to apply eccentricities to kind of try keep the foundation in check when it comes to almost equally distributed soil stresses. So there are some disadvantages of having a fixed support, besides the practicality of adding welds and so on. But well, we are here to investigate that, so let's dive into it. Now, there are some supports that are easily considered pinned. There is a golden rule I know from my own work, and tell me if you agree with it or not. There was a golden rule that if the bolts are inside the section, this is definitely a pin, meaning that the bolts have a moment arm that is smaller than the moment arm with the two flanges, then this is usually a pin. Something like this is a pin, something like this is a pin, and sometimes you would have a deliberate pin. Now this, you cannot argue with. This is absolutely a pin. But I know what you're thinking. You might think, hey, wait, there is actually friction. Oh, come on. The friction is not really that big compared to the moments that you will have. Now, there are also other supports that are considered traditionally fixed. You will find those fixed supports everywhere. If you walk on the street, any lighting fixture in the street is going to be having if it's made out of steel, and usually they are, then it will be having a fixed support here due to static equilibrium. And you will notice that those fixed supports usually have stiffeners, as we have said, a lot of them, and their bolts have those J anchors to make sure that they don't get pulled out. You might have a uniaxial bending, a biaxial bending, and you would have to design those things. Notice that because you have stiffeners, suddenly you have new things you need to check in the column section to make sure that those stiffeners don't buckle the flange. Now for this is traditionally considered fixed, that's traditionally considered pin. So those two things kind of have their own classification. The thing that becomes a gray area is this one. Is this fixed or is this pinned? Now, I'm not going to take a side here. This can be endlessly debated and everyone can get his own ideas about this. And I'm really interested in you telling me in the comment section how your experience with regional application of pin versus fix is, because I want to see how other regions deal with it. Now, this is what I like to call the gray area. And is this a fix or pin support? And here we can say it depends. It depends. And by the way, even this depends, because if the foundation is not good enough to be able to carry the moment, then this becomes a pin support. I shall show you how the foundation looks like for a fixed support in the next video in Robot. So what about this gray area? Well, it depends on the base plate versus column stiffness. Luckily for me, the Eurocode talks about it. Now, from various resources and references, they basically categorize the base plate or the column base into rigid, semi-rigid, and pin. And usually, I've talked to a lot of professionals here, and they told me that usually they consider this to be semi-rigid to pinned. But of course, I'm not here to take sides. I'm here to speak facts. So, there are two categories or two classifications depending on your frame. If you want to dig deeper, this goes into the 5% rule, in which there is a effect of 5% of the column strength. And it's a long story. I really encourage you to read the references on that. But alas, if you have a sway frame, which is this one, then this is your classification. This domain is rigid. This domain is semi-rigid. And anything else is just plain pin. And you don't even need to check it because you can easily see if it's a pin. I mean, those are obviously pins. Then you have a braced section. And in the braced section, this becomes the rigid zone. You can see it's larger. This becomes a semi-rigid and so on. Notice, I haven't talked about what those mean. SJ initial, this is the secant stiffness, in other words, stiffness of the base plate of the column. So this is the stiffness, rotational stiffness. meaning, for example, Newton meter per radian. Now you can see that if the base plate stiffness is larger than a certain value, then it becomes fixed. If it's smaller, then it becomes semi-rigid or so on. This is actually the rotational stiffness of the column with some modifications. You can see that the base plate needs to be massively larger than the column stiffness to be able to count as fixed. This is, of course, for a unbraced frame. Sway sideways. If you have a braced frame, then yes, still you will have to have a massively larger stiffness, but at least it's 12, not 30. So there's some reduction here happening. Now the big question becomes, how do I calculate SJ initial? There is a big problem in the Eurocode that talks about the SJ initial. The big problem is that, yes, there is an equation to calculate the stiffness of the base plate, but the equation that is given gives you a catch-22 problem. In other words, it asks the question, who came first, the chicken or the egg? Now, I think I said this before, but I will answer the question again. The egg came first because reptiles were laying eggs way before chickens even existed, so the egg was first. Anyway, scientific shenanigans aside, I want to talk about the catch-22 problem that is SJ in the Eurocode. SJ depends on the applied moment and applied axial force. Where is the problem? Well, the classification depends on the applied loads. The applied loads here are the reactions of the support, and it also depends on some aspects of the column seen here. Now the problem here is, how do you get the applied load and how do you know what the column is? You get the applied loads by performing an elastic linear analysis. Last time I checked, if you want to perform analysis, you have to assume a support. But you don't know the support because we're still thinking about it. So to calculate the applied loads, we need to apply the support, but we are still asking the question, should I apply pin or fix? This means for this approach to work, we need to perform iterative work. You apply a pin support, check if you can make it rigid or semi-rigid. You apply the rigid or semi-rigid and check, and back and forth until finally nothing changes. And then you say, I finished. This is quite hard and quite time-consuming. So another suggestion for the preliminary design to kind of avoid the catch-22 problem is to use the formulas developed by Steenhuij. I don't know how to read this. It's in the reference. And here he basically tries to estimate via the dimensions of the column and dimensions of the base plate. An initial estimation of the base plate stiffness is the elastic modulus, which is 200 gigapascal, multiplied by Z. Z is the moment arm. You can see there are multiple cases, but usually I like to say that the lever arm is between the bolt under tension and the flange under compression. Now it's a long shot, because it depends exactly on how the column base plate is, if it is dominant in compression or dominant in tension, meaning if the axial forces are dominant, then your base plate moment arm becomes the flange distance, and if it's moment dominated, then it becomes bolt to flange. How do you know this? You think we are back into a catch-22 problem, but actually we're not. As a rule of thumb, if you have a fixed support, then it is usually moment dominated if you have not so many stories, because usually this is like 10 meters or 6 meters. Usually you have a large span, meaning that the moment here is going to rise high, which causes extra moment on the column, which will be resisted by the foundation. And usually in a single story frame, I'm expecting bending moments to dominate. In a high-rise building, I'm expecting axial forces to dominate. Now, this is my humble opinion. Feel free to disagree with me. Now, there is another approach. So this is basically how I can find SG initial and check what can I assume, rigid or semi-rigid or something. Spoiler, usually it is semi-rigid at best. This support is semi-rigid at best. This support is traditionally taken to be fixed, and those supports are traditionally taken to be pinned. So this support is at best semi-rigid, and I will give you an Excel sheet that our teaching assistant has has quickly prepared so that you can check and see for yourself. Now notice, this is only an approximation because it does not depend on the applied loads. It just depends on the broad classification. And even the reference here makes something strange. Like, this is something that I did not understand from the reference itself. Let me show you. So I think there is a problem in the reference. The reference says here, this is the equation I took, and there is a Z here. However, here, he says there is an R, and he wants to show you the lever arm. And it tells you the lever arm is the distance between the anchor bolt and the flange subjected to compression. So where is the anchor bolt and where is the flange subjected to compression. And for some reason, he tells you this is the lever arm. Now, this lever arm doesn't make sense to me because I don't see an anchor bolt. Okay, here is an anchor bolt, but I don't see a compression flange here. And this doesn't make sense to me because I don't see an anchor bolt and compression flange. The only drawings that make sense to me are those. That's why in the slide I showed you those. Because maybe they missed something here. So I don't know. I should email them, I guess. It tells you the distance between the anchor bolt, which is anchor meaning tension, and the flange or the compression, which is basically the lever arm of the compression and tension forces, which is the moment. Perfect. So I think this makes more sense. This is making more sense to me. Back to our presentation. There is another empirical approach. If you don't want anything from the shenanigans, the report suggests a certain way. I never tried this before, to be honest. I kind of understand what he's trying to do. What the report in the empirical approach tries to do is it argues that there is no perfect pin and there is no perfect fixed support, and I agree with that 100%. Sometimes if you really need some stiffness, then this might come into handy. The idea says, hey look, if you assume that your support is going to be a pin, how do you deal with it? Well, first of all, when you perform the elastic analysis in Robot, for example, you assume it to be pin, pure pin, no moment. You do your analysis and you calculate your design, ultimate loads, and design your sections, and everything is fine. Now, when you want to check the frame stability, you could assume that this pin isn't actually a pure pin, but it's a spring support with a spring stiffness of 10% of the column stiffness for frame stability, and for deflections, 20% of the column stiffness. I understand what he's trying to do. He's trying to be safe and considerate. So he's trying to be safe, but not too safe. When it comes to life and death situations, i.e. ultimate loads and design of sections and base plate dimensions, he is applying a pure pin, which makes sense because it maximizes the design for life and death situations and includes the simplest of foundations that is easy to implement and is well known. Now, when it gets to serviceability, then he actually considers the idea that a pin is not a perfect pin and says, I'm going to use 10% for frame stability and 20% of the stiffness of the column for deflection, meaning that instead of a pin, he will replace it with a moment spring with a spring stiffness of 10% of the column if he checks stability and 20% if he checks the displacement or deflection. I kind of understand what he's doing here because he wants to be economical yet safe. If you have a rigid base plate, well, in reality, there is no 100% rigid. This is written incorrectly. What he says here is, well, if you want to perform the ultimate design, assume a stiffness equal to the stiffness of the column, meaning if you want to design the frame, don't put a fixed support here. Put a spring with a stiffness that equals the stiffness of the column. Is this more safe? For the sections, usually yes. Because if you don't have a spring at the support, then the moments here increase and the column becomes bigger. If you want to check the deflections, then you can assume fixed support. So I hope this makes sense. I've never used this before. It's a suggestion by the Steel Construction Info. I kind of understand what he's trying to do. Feel free to use it, of course, on your own responsibility. This report doesn't come from just out of nowhere, from thin air. No, actually, this has a quality record in which the technical content was endorsed by some of the partners. One of the endorsers is the Rheinisch-Westfälische Technische Hochschule in Aachen. Das ist in Deutschland, in der Nähe von der niederländischen, belgischen, deutschen Grenzen. This is one of the best universities in Germany, and it's situated near the borders, the shared borders of Netherlands, Belgium, and Germany. So having this endorse, this record, for me, is something bigger. It's something big. Of course, here the Steel Construction Info endorses it, so I think this is a good thing. Anyway, this report tries to use the things established in the Eurocode and make it become practically available. Feel free to use it if you want it. What would I do if I want to analyze a frame? Here is my framework for you, like the workflow that I would do if I would want to design a steel frame. I don't want to use the empirical approach because I've never done so before, but I want to do the following. First of all, I would calculate the applied loads in the frame. Then I would model the frame, assuming a pin base. That's my first assumption, because this will usually cause larger steel sections, but maybe reduce the size of the support due to no moment being applied. However, it's not a problem, because if I assume a pin, then I will make sure it's a pin by putting the bolts inside the section, or making sure that the base plate stiffness is not stiff enough to be semi-rigid. I would perform the design of the sections and apply the new sections. Once I apply the new sections, I need to recalculate again, because how do I perform the design? By calculating the frame. So I need to assume a section to begin with. When the section changes, the stiffness changes, which means the moments change, which means I need to recalculate the frame and design again, and do it sometimes until I'm satisfied. Next, I would perform the design of the base plate and the reinforced concrete foundation. This typically ends the design of a steel frame. Of course, I also should design the connections. However, here's the thing. If I suddenly say, hey, I want to utilize a rigid or semi-rigid base plate, for some reason, because maybe the deflection is too large, and there is no way to decrease the deflection, then there are two options. Option one, I would choose to add the stiffeners, like apply the original base plate, meaning with stiffeners, or I would choose to go into the gray area, which has this base plate with the bolts. I need to make my choice now, because I'm going to redesign the base plate later in Robot, and my decision here will reflect in the choice of the base plate later. So my decision needs to be taken right now. If I take a decision to go fully rigid, this means when I design the base plate, I need to make sure I add stiffeners. If I say I want to design without adding stiffeners, then when I design the base plate, I will add no stiffeners. If I choose the gray area, then I must check the stiffness of the base plate and make sure I'm allowed to use the rigid or semi-rigid approach. Finally, I analyze and design and make everything, but I check the reinforced concrete foundation, and you may not like what you will get from the reinforced concrete foundation. This is the make or break moment of your rigid support. So usually I suggest when you reach this point to kind of save your file and then test. So okay, let me show you the Excel sheet the teaching assistant has prepared, which I will be uploading, and the link is in the description. Notice this Excel sheet has been prepared in one night, so the accuracy has not yet been checked. I would rather ask my dear viewers to use it at your own discretion and tell me if there is any problem, so that I can scold the teaching assistant if you made a mistake. Here we are in the Excel sheet. The Excel sheet is based on the NCCI. I need to zoom in maybe for you to see. The Excel sheet is based on the NCCI, column-based stiffness for global analysis. The formula for preliminary base plate stiffness is at section 4.2. This is the one where you need to find the base plate stiffness. Now here, he wants EZ square and TFC over 20. The E is easy, that's the elastic modulus. TFC is easy, the base plate thickness. 20 is a value. But what is Z? Z is the distance between the anchor bolt and the compression flange. So how do you calculate that? Well, it is the distance from the center of the section to the middle of the flange, plus the distance from the center of the section to the bolt. Z is the distance, I repeat, from the center of the section to the center of the flange, plus the distance from the center of the section to the bolt. This means that I need to know what my section is. I'm assuming the HEB section 200 here for this example. So of course, the height of it is 200 millimeters. The flange thickness is 15 millimeters. The distance of bolts, what I mean by this is the distance between the compression bolt and the tension bolt is 300 millimeters. Should be larger than the section because we want to be in the gray area. And the elastic modulus is 200. How do I calculate Z? Z is calculated by saying half the distance of bolts, because if the bolts are 300 millimeters apart, then from the center to a bolt is 150. That's why there is a half here. And half height minus half thickness, because I want to go from the center to half the flange. So I need to take half the height of the section minus half the flange, and that's what you see here. This will give you the Z. Then I multiply them together, making sure I don't blunder any units. So the elastic modulus in gigapascal gets multiplied by 10 power 9. The distance Z is divided by 1,000 because meters and millimeters. Similarly, the thickness is divided by 1,000, and this will give you a Newton meter per radian, which is actually transformed into kilonewton meter if you want. I transformed it here because I want to help you use it if you want to apply a semi-rigid support. The classification by stiffness, this is where those limits come into play. The inertia of the column is 57 something. I've taken it for my reference because we used this column. The length of the column is assumed to be 4 meters, which will let you calculate the sway rigid limit and the braced rigid limit, depending on those things. 30 I over L. So you can see 30 EI over L with unit manipulation. Now, based on this, you compare this value and decide. This value is lower than both of them. So in both cases, you should assume a semi-rigid or pinned support. So in both cases, this base plate is not enough. You can increase the base plate by increasing the bolts distance. However, this will cause a problem because if you increase the distance of the bolts, then the base plate suddenly starts to bend and you need to have a thicker base plate. I would rather, in this case, if I feel that my base plate is hard to be considered rigid, then I would basically go to the traditional rigid supports, meaning with stiffeners. You know what? Just leave this gray area and either choose pin or rigid. Remember, if you choose rigid, then there is something about the foundation that needs to be checked. We shall do this in Robot in the next video. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a semi-rigid shout out to my dear channel members in the contributor level and the helper level, whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing and commenting, especially subscribing because it helps increase the reach of my channel. As per usual, this is a Civil Engineering Essentials channel and we'll catch you in the next video. Bye bye.